Hi, my name is Shaquille Sarathia. I'm with Fox. Before I get started, I will say that, yes, I do have my friends who call me Shaq, and I have no relationship to Shaquille O'Neal. Although we do probably have the same free throw percentage, so it's about that. So anyways, I'm with 21st Century Fox, and about 21st Century Fox, if you guys don't know, we're kind of a small company, global portfolio of cable and broadcasting networks. I just pulled that blurb from our investor page, so you can read that if you want. But the highlights here is that we have channels across the world, some very popular ones, especially domestically, Fox Sports, FX, National Geographic, things like that. So that's 21st Century as a whole. And then the specific organization inside of Fox that I represent is the Digital Consumer Group, DCG. And we're an organization that's really just tasked with the digital delivery of our content to consumers. So on the right there, you can see a couple of images of what we're delivering. So what that is the Fox Now application that you can download on your iPhone, Roku, whatever, or just go to it on the web, and you can watch Fox content with your cable provider. So if you have Comcast, DirecTV, what have you, you can log in with your provider and watch the content, and there's also free content there. So this is the application that we are actually delivering to our end users. So there's really two components of it. What you're seeing here is obviously the front end. And because we have a number of front ends, whether it be web, mobile, connected device, what have you, we deliver everything through a common API layer. So what I'm really going to talk to you guys about is the common API layer and how we deliver that. Now, there's a lot more services that we end up utilizing. However, I just wanted to kind of show how we're delivering it as it relates to this presentation and to ECS in general. So first of all, everything that we're doing, all of our experiences are running out of AWS. We're utilizing API Gateway to actually deliver all of our APIs. We are a microservice architecture with our services that are written in Node.js and Go. And we have different teams that deploy things differently. We have some teams that, mostly we're utilizing Terraform, but we do utilize CloudFormation for certain things. Some teams deliver multiple services at once. Other teams deliver single services. And this is going to be important because we'll run through some of the challenges here. And then everything is delivered through ECS. So we're fully Dockerized, and we're delivering everything through ECS. So some of the challenges that we've run into, and I think Werner's kind of spoke about it a little bit this morning too, that as you move forward, you kind of have to evolve your architecture, right? So every time you kind of step through, you evolve. So our architecture was probably initially developed about a year and a half ago, and so as we've kind of grown, more people coming to our applications, we've had to also evolve. And so a lot of the challenges that we faced has been things like, well, we do have a microservices architecture, lots of services, and we're utilizing bridge mode. And we've got hundreds of instances, right? So that's a scale issue there. Some of the other challenges were that teams needed to be able to determine how to route. They need to write services too, but route an individual service between a blue, green, purple, orange, red, what have you, deployment. We also needed to be able to route a single request anywhere through the stack to a specific service. Maybe for testing, it might be for some type of a feature. Imagine if you're deploying a feature to 2% of your users, and that feature is potentially a microservice that's 3 layers deep. How do you make sure that you've selected that feature up front, but now you've routed it to the right area? So those would be challenges too. We have to maintain multiple versions of the same service. Because, as many people know, you run your apps, not everybody updates at the same time. So we have to maintain different versions of our APIs. We're very ephemeral. We want to be able to deal with failure, pretty much at any level. Services, containers, anything can go, and we have to be able to manage that. So, what did we look at in order to kind of deliver some of these things? So, again, one very common way is put some ALBs in front of the microservices, but you run into certain limitations. One of the limitations is that target groups will have a limit of 1,000 targets. You can change that. We have, but that's something you have to be cautious about. This does end up leading to hundreds of ALBs, and if you've worked with API Gateway, then there's a lot of complexity in the integrations, and then you've got development, stage, load, production, all these different environments that you might be going to. So you've got tons of variables there. So it just, I think you could definitely deal with it in terms of the automation, but it does start to get fairly complicated. Another thing that we looked at was saying, okay, well, let's just get rid of that, and let's talk directly from one microservice to another microservice utilizing DNS. Another way that you can do that, it does, I'm sure there are some systems engineers in here, and as any systems engineer has known, we run into many debates around naming schemas and what metadata you want to put into the DNS structure, and at some point you forgot to put this one metadata, and now how do you do that? You change the whole structure for everybody. So those are going to get very complicated to try to think those things out. So another way was to say, well, let's take something in between here and utilize software to create a service mesh. And this is actually what we ended up doing. So what is a service mesh? It's a dedicated infrastructure layer for making service-to-service communication safe, fast, and reliable. So what that means is you are going through some layer of software that can find your services, right? So utilizing some form of service discovery allows the service mesh software to route requests to a healthy instance of a specific service. So if you've got service A trying to talk to service B, we would go through the service mesh layer. It would find out where service B is. Again, you have to do some type of service. I should mention one thing really quickly is that most people will, you talk about a microservices architecture, and we always talk about it at the application level, that we're delivering our application through microservices. But you can actually take that a step deeper into the stack and almost think of your infrastructure as microservices, which is and that's the reason I'm really only talking about the service mesh, because that's that layer. Your service discovery is a different microservice, if you will. Your registration into service discovery is a different microservice. So you can really kind of just plug in different pieces that may make sense. And that's why we're kind of did it like this. And the software that we elected to utilize is Linkerd. There are other bits of software that are out there. Two that come to mind is Istio. How do you pronounce that? Istio. Envoy. So there's a lot of other things that are out there. We chose Linkerd. It fit a lot with what we're doing. It fit with our microservices infrastructure layer. But by all means, it's just a concept there. So let me show you at a very high level. And the next couple of slides are going to be more around the actual diagrams. And I was kind of debating, do you show high level and then detailed? Or do you go detailed and then high level? Neither one really seemed right. I flipped a coin. It landed on heads. Heads is high level. So there we go. So this is what kind of our from the top down looks like. So we'll have the internet or applications that are attached to the internet, if you will. They will go to Amazon API Gateway to hit a specific API endpoint. From there, now everything goes through a single load balancer. API Gateway has to talk to a load balancer, so it goes through a single load balancer. And one comment I want to make here is that I don't know if you guys have used network load balancers at all. But if you are doing classic ELBs and trying to do TCP so you can get directly to your instances, I would highly recommend NLBs. They're a little bit lighter, faster, and they're pretty cool. So we have switched that over to an NLB now, which basically load balances across a layer of Nginx servers. And that's all running ECS. The communication, if you look at it, if you're familiar with it, NL right now, and I'm sure that the folks at Amazon will eventually fix this, but currently API Gateway can only talk to a publicly exposed internet-facing NLB, and so, or internet-facing load balancer, not yet a VPC endpoint. So the way to secure your communications is through a client certificate. Again, ALBs actually can't process client certificates, so if you're actually in this mode, you're either utilizing classic EC2 or ELBs, or you'd want to go NLB and have to terminate SSL on your instances. So that's what we're doing. Nginx effectively terminates SSL there, and the network load balancer lives in the public subnet. Everything there, and I kind of noted there that while they look different here, they could be the same set of physical servers. It doesn't really matter. You can choose, there's definitely reasons why we would make those different in the sense that you may have different networking needs. You can use different congestion algorithms on different ECS servers if you need to reduce time to delivery and things like that. And then below, we have all of our Fox DCG microservices. So to go into the, we'll note that this all lives in a single VPC, and we have multiple subnets. All the ECS servers live in a private subnet, and the only thing that lives in the public subnet is the load balancer. So now the detail of this is how do the services communicate. So I pulled, again, there's a lot in here. There's a lot of other things that actually live there. So I pulled all of that out to kind of just show the pieces here that actually we're utilizing for this. So the way that it works is that, again, I mentioned all the ECS nodes live inside of a private subnet. It could be multiple AZs. It could be a single AZ, what have you. So when service A wants to talk to service B, what we've done is we've loaded linkerd onto every ECS instance. So there's one linkerd per instance. So every container, we don't run it as a sidecar. We run it as a, on an instance basis. So every container talks to the local linkerd. One of the reasons why is once you start getting, hitting a lot of scales or hitting a lot of containers, you'd have a ton of sidecars potentially. So right now we just run a single one. That could change. Again, not a hard and fast rule for us. It talks to linkerd through the Docker bridge. So that's how it knows. Every instance finds its Docker bridge. In order to talk to linkerd, it talks to it on its Docker bridge, and off it goes. Linkerd will say, OK, you want to talk to service B, right? And what it'll do is it'll find a healthy instance, right? It'll go and basically query our service discovery backend. It will find a healthy instance, and then it'll proxy the request over to that instance. That task will then do whatever it needs to do, return back to linkerd. Linkerd will come back to the service, and the service is none the wiser that it actually went through anything. It just understands that it made a request, and it got serviced. Now, so that's kind of the implementation details on that. This next slide here is basically saying everything that I just talked about. I tend to do this because if somebody watches it on some YouTube, at least it's there and you don't have to hear the audio. I know my voice gets annoying to me too. So ETS instances reside in private subnets. Service containers are deployed through ECS. Container instances utilize the ECS optimized AMI. And then we add linkerd through our user data. So it's actually also deployed as a Docker container on the instance. Servers send all service-to-service requests to their local Linkerd instance. All services have a name that other services can talk to it. And then it uses that name to find the services routing in its delegation. So if you look at that delegation, and well, it's in yellow, orange, I don't know what color it is. You'll see that the way that it works is that we have service A underscore version 1, right? So we could have version 2, version 3. That's the name of the service. Now, the way that we can achieve blue and green deployments, again, would be by setting it to saying 95% of the requests to this service, service A underscore v1, should go to the blue version of service A, and 5% should go to the green version of service A. So the teams, the individual teams, can actually control this, and you can set blue, green, orange, purple, whatever, and they can control the percentages up to 100%, of course. So some of these things that, some of the reasons this could be utilized is that you're rolling out a new version, you want to check it out, verify that your blue version, your green version is working right. You look at your logs, make sure there's no additional errors, things like that. Another thing that you could do is to do run experiments. I think during the talk today, Netflix talked about they run chaos experiments, right? So that could be something that says you have a 2% of your requests are going to this service, which is actually creating different problems maybe, and you want to see how your upstream services react. So it gives you a lot of flexibility there. The nice thing also about that is not a hard and, in Linkerd, that's not a hard and fast rule that's the only delegation tab that it'll utilize. So what you can actually do is on a per request basis, you can actually send a new thing. So for example, let's just say I wanted to route this one request for service A to service A v2 because I want to test this in production. I have maybe some feature flagging. I've done something there. I can actually add a header to the request that's way at the start, and that header will propagate through the entire system, so it doesn't matter what service ends up using that service, it'll make sure that it goes to the new service. So there's features like that that we were able to get out of this. The other thing is that the way that we've architected it is that the ECS instances are entirely horizontally scalable and use EC2 auto-scaling groups to scale out when it needs more memory, more CPU, or anything like that. So it scales out horizontally because everything is contained in a single ECS container instance. It pretty much scales for pretty horizontally. So what we got through this was that we gave the teams the ability to instantly change routing for a microservice. By modifying that delegation tab for a service, a team can decide where the traffic should go. Another feature that we got is Linkerd has some resiliency functions built in. So it can retry, if you tell it to, it can retry idempotent requests. So in our world, that's basically any request that's not a post is considered an idempotent request. So that's how we design our services. And if one service returned one instance returned to 500, maybe it's just in the process of failing or anything like that, Linkerd will retry that individual request against another instance. So your calling service actually never sees issues. So it's got certain features like that built in too. It can tie in with the service discovery backend. So it'll immediately find healthy containers depending on your backend. It could be any backend. It could be DNS. We utilize console, but it can be pretty much anything, Route 53. It could be anything that you need it to. Another nice feature of Linkerd is that it's able to determine slower instances and route fewer requests to these instances. So if you've worked in EC2, if you've worked in a container world, you will invariably run into a noisy neighbor problem. So being able to look at the latency of the request coming in from a particular task is nice to be able to say, hey, I'm just going to give this one fewer requests so that I'm not making that instance even worse. So this is all nice. It's never a great world because there are always challenges to be solved. So what does the future hold for us in terms of challenges that we plan to tackle? One issue is obviously security. Security is still a challenge in this environment. Task IAM roles are great, but they're they only take you so far, right? They can talk. You can limit your exposure to your data sources potentially, like DynamoDB or something like that, but not necessarily to other services, right? So as kind of Deepak talked about task ENIs, that's a big win potentially for PCI or PII data, especially if you're under compliance regulations, because half the time, most people know it's a check the box. Are you doing this? Do you have an ACL? No. Well, then that doesn't, so being able to have that definitely helps. Another thing that right now Linkerd doesn't really natively understand how to find the closest container. So it does do some of this through the latency routing, because it'll try to pick containers that are lower latency, but it doesn't really understand that, hey, I wanted to talk to a container that's maybe on the same instance or in the same availability zone and then in the same VPC, right? Although there are some tricks that we can do with the service discovery backend, and again, because we think of it as a kind of a microservice type architecture, we can do that. So that is pretty much what concludes my portion of this. I think thank you would be in order. It would have been really awkward if none of you guys showed up and we were speaking to an empty room. So definitely thanks for coming, and we're around for questions.
Yeah, thanks a lot.